We are live. We are live. Yeah, it has gone live just now. लाइव है यूट्यूब में. Sorry, what's happening? How is that possible?
Because of the sustenance of the human race. Now I'll try to give a slightly different perspective by an anecdotal story energized from a writing of Prakash Iyer in Business World. The story is about the river Choluteca in Honduras, in Central America, a region notorious for storms and hurricanes. They decided to build a new bridge over the river Choluteca in '96. They wanted to ensure it would withstand the extreme weather conditions. A Japanese firm was contracted to build a solid bridge designed to withstand powerful forces of the nature. The Choluteca Bridge, a modern marvel of design and engineering, was thrown open to public in '98. Uh, but then, few months October '98, there was a heavy downpour and hurricane called Mitch that hit Honduras. There was 75 inches of rainfall in a period of 4 days. Normally, that amount was for 6 months for them. 6 months of rainfall for them. A lot of flooding. The road coming to Cholateca bridge disappeared. The road going out of Cholateca bridge vanished. There is no sign of any road coming to this particular bridge. Moreover, one more thing happened. During this flood, the river changed its course. It started flowing beside the bridge, not under the bridge, and resulting in the bridge of nowhere, bridge for nowhere, bridge is standalone. So this exemplifies, demonstrate that while trying to create robust solutions, infallible solutions, optimal solutions, we forget about, we ignore the other possibilities because I am a proponent of systems understanding. So you cannot focus on only the problem at hand. You have to anticipate what else can happen. So this is a wonderful metaphor that can happen to anybody in our lives, in our career, in the business process. While addressing the solution can change. The goalpost can change. So the bridge was designed to withstand all the natural forces, but we forgot to design to adapt to the scenario. So sustainability solutions is addressing the sustainability issue, but at the cost of inefficiency. Cost inefficiency. Sustainability solutions always associated with building inefficiency. Now, if you try to optimize a solution, it is also resulting in vulnerability. It induces structural instability. So, don't, as an engineer, don't assume that the optimization technique and the optimal design, optimal way of doing business is many times take you to a different level. So try to have a holistic, try to build a holistic view, understand that adaptive control. You have to develop a respect for details, a respect for measurement, anything and everything. As an engineering graduate, you should bother about measuring anything and everything, and also develop a eye for or practice closed loop, adaptive control, and feedback. So if you're trying to create a closed loop control that is energized by feedback, but you're not doing anything. There's an input process, there is an exit process, there is a result coming back and giving feedback, but nothing is happening. But if you introduce an adaptive control in between, then all the feedback will be analyzed and corrective measures getting in place. So develop a eye for measurement and feedback. Understand more about feedback control in any area of human endeavor. Moreover, I also like to sensitize you about the natural causes like pandemic, like tsunami, like earthquake, like flood, drought. These are natural phenomena. It go beyond human comprehension. It go beyond a collective comprehension, collective intelligence. The technology development, all the modern technology, all the cloud computing, all the deep learning technique cannot prevent this. What we can do is going forward, we can develop a lot of mathematical models, mental models, and mathematical models which can predict the advent of the coming of these natural causes having devastating effect on the human life and society. But even now, we are too small. Man is too small to address the issues bringing by natural causes, like I mentioned. What we can do is we can remain focused to anticipate this kind of recurring of this kind of natural causes and developing, mitigating, and develop strong, robust methodology techniques to predict it and develop mitigation techniques. I congratulate everybody once again. I express our sincere gratitude to the speakers, Professor Elizabeth, Professor Neeta Mehta. Thanks a lot. Wish you all the best. Thank you.
Thank you, Principal Sir, for such encouraging words. We will now begin with our first session for the day. Joseph, speaker for our first session. Dr. Elizabeth Joseph is an associate professor at the Department of Chemical Engineering of the Thadomal Shahani Engineering College. She is invited as visiting faculty for a course on separation technology at the Institute of Chemical Technology, Mumbai, a number of times. She also is the faculty coordinator and internship coordinator of the department. She also chairs the Women Development Cell of the Institute. She is a member of various other committees of the Institute. She has done her BTech in Chemical Engineering from Thadomal College of Engineering, Kerala. Her postgraduate and the doctoral degrees are from the Institute of Chemical Technology, Mumbai. She started her career at the industry and switched over to academia since 1994. She has presented her research work on carbon dioxide absorption at various international conferences and published papers in this topic and others in national and international journals. She has authored a book on generic skills. She is a life member of IST and IITNG and networking member of UK CCSRC, that is UK Carbon Capture and Storage Research Center. She has also delivered invited lectures at other forums like the UN Tolerance Day discussion held in Mumbai and on values of life international. She was awarded minor grant of research on study of phase criteria for carbon dioxide absorption by the Mumbai University in 2015 and Best Poster Award by the Royal Society of Chemistry at the 6th International Conference on Advances in Energy Research in the year 2017 on the topic of kinetics of polyamine activated solvent for carbon capture. We welcome you, ma'am, for this session. Thank you for the introduction, Dr. Nita Mehta. Good morning, good evening, everyone, depending on from where you are hearing from. Thank you for tuning in to this webinar. We at Thadomal Shahani Engineering College, Mumbai, Department of Chemical Engineering, is happy to see so many of you sign up. We genuinely hope this webinar finds you safe and healthy in these times. The webinar caters to the broad spectrum, including practicing industry personnel, students and faculty of sustainability, environmental studies, chemical engineering, and students aspiring to join chemical engineering. For this purpose, the presentation dioxide mitigation. In this presentation, I will focus on carbon dioxide as a greenhouse gas. Then we will look at carbon capture from industrial processes as a mitigation method. Next, we will look at the purpose by which carbon dioxide is captured. Finally, we will look at how the process can be designed and where it has been implemented. Now, what is sustainability? This picture gives us a hint. Generation together. I would like to read sustainability as sustainability means meeting our own needs without compromising the ability of future generations to meet their own needs. The three pillars of sustainability are society, economy, and environment. My focus for the day talk is the environmental aspect, environment and sustainability. When we talk about environment and sustainability, the term that pops up in anyone's mind is global warming, climate change. What is responsible for that? The impact of global warming is far greater than just increasing temperatures. Warming modifies rainfall patterns. Warming amplifies coastal erosion, melts ice cap and glaciers, alters the ranges of some infectious diseases. Some of these changes are already occurring. Which are the primary greenhouse gases that are responsible for global warming? Water vapor, carbon dioxide, methane, nitrous oxide, and ozone. The larger the global warming potential, the more that a given gas warms the earth. Anthropogenic emissions of water vapor are small in comparison to the large evaporating emission of water vapor from the ocean. Methane, nitrous oxide, and ozone have a much larger global warming potential than carbon dioxide. Then why is carbon dioxide so important? It depends on how long it stays. The period that the gas is present in the atmosphere. Carbon dioxide stays for thousands of years, unlike the other gases. Therefore, its concentration at a given time increases in the atmosphere as man-made emissions happen. So we know that when we talk about the greenhouse gas and global warming, carbon dioxide mitigation is so crucial. Let's look at this pie chart, which gives us each country's share Very obvious, 28% of the emissions are from China, followed by 14% from the United States, and India contributes 7% of the emissions. Today, we are going to focus on carbon capture from industrial emissions as a way of mitigating the concentration of carbon dioxide in the atmosphere. What are the sources of industrial emission of carbon dioxide? Carbon dioxide is emitted from large stationary groups. The largest single source of carbon dioxide are the conventional coal-fired power plants. Cement manufacture emits around half a ton of carbon dioxide for every ton of clinker. What about refineries? For 300,000 barrels per day refinery, the carbon dioxide emissions are in the range of 0.8 to 4.2 million tons per year. The iron and steel industry are one among the largest energy consuming manufacturing industry. Energy, again, that has to be highlighted. For every ton of steel, around 1.8 tons of carbon dioxide is emitted. Therefore, much effort has been put into the development of technologies for the capture of carbon dioxide from process stream. This is the closed loop absorption-desorption system, where absorption occurs in a pack tower at low temperature of around 40 degrees Celsius, and desorption of carbon dioxide loaded absorbent is accomplished at higher temperature, around 100 degrees Celsius. This is a common process configuration. The products of combustion of coal from the power plant, we need to prepare steam and to vaporize or evaporate water. The process requires energy, and the energy is supplied from the combustion process. The flue gas, the product of combustion, carries large amount of energy. After the energy transfer to the power plant, in the economizer, then the evaporator, the superheater, and finally the air heater, the flue gas which leaves the power plant carries around 14% carbon dioxide. There are other gases along with it. The carbon dioxide capture plant focuses on absorbing this carbon dioxide and making the gas within permissible limits of the environmental regulation so that it can be exhausted into the atmosphere. Now, the carbon dioxide laden exhaust gas is sent to the absorber. The absorber is a tower, or it is a column, a long cylindrical vessel, a very tall cylindrical dioxide laden gas is fed to the bottom part of the absorber, and there it comes into contact with the absorbent solvent, which is fed at the top of the absorber. The gas, carbon dioxide, gets absorbed into the solvent. Now, the solvent is rich in carbon dioxide. The other gases, which were part of the inlet gas or the exhaust gas, which came from the power plant, they are now clean or lean with respect to carbon dioxide, and they are exhausted from the absorber as clean exhaust gas. What happens to the concentrated absorbent solution? Concentrated or thick with respect to carbon dioxide. It now passes into a regenerator, which is also a column, which is fat. During absorption, the carbon dioxide is transferred to the absorbent, and now the absorbent solvent needs to be regenerated to reuse it again for further absorption. The regeneration is done by supplying heat, which is usually done with the help of steam. So here, the circles that you see are heat exchangers. We need to supply heat. Therefore, we try and heat the solvent, the thick solvent or the absorbent, which is fully laden with carbon dioxide. We try to heat it by exchanging it with the lead solvent. Once the absorbent solvent is heated, the carbon dioxide is stripped off it. The solvent is stripped of the carbon dioxide. And now the solvent is again lean with respect to carbon dioxide and can be sent back to the absorber. What happens to the carbon dioxide? The carbon dioxide is separated from the top of the regenerator. It is compressed and stored for either the manufacture of a chemical like soda ash, methanol, or for a fertilizer like urea. And if these plants are not nearby, we do not want to transport it. It may not be economical to transport it to long distances. Carbon dioxide can be used for oil recovery. Or if none of these options are economical, then it is stored in geological storage underground. This is how an absorber regenerator system would look like. This gives you an idea of the shape and size of the system. Now let's look at the solvent or the absorbent that can be used. How is it regenerated? As I said a while ago, the most common method is by heating it. solvents. Which are the solvents that I will be using? The solvents may be classified as physical solvents and chemical solvents. What is physical solvent? Physical solvent is a solvent which absorbs the carbon dioxide without having any chemical reaction, which means the operation is purely physical absorption. The driving force is the concentration difference of carbon dioxide or the pressure difference, which necessitates the need of having a high inlet gas pressure. What do I mean by a high pressure? For a physical solvent, the inlet gas pressure should be around 414 kilopascal. The standard atmospheric pressure is 101.325 kilopascal. For atmosphere pressure, which makes it a limitation, especially for the exhaust from a power plant, where the concentration is around 14% by volume. Some of the physical solvents are water, methanol, polyethylene glycol dimethyl. When is the chemical solvent used? Chemical solvent is the option when we have a low concentration of carbon dioxide. The prime requirement for regenerative carbon dioxide removal is that any compounds formed by the reaction of carbon dioxide and the absorbent solution must be readily dissociated. Alkanolamines, alkaline salt solution, and amino acid solution are some examples. Monoethanol amine has high reactivity towards carbon dioxide. It has a good rate constant, but its properties are not favorable with respect to degradation. Therefore, there are other options of using tertiary amines like methyl diphenol amine, which we commonly call as MDA, or a tertiary green alkanolamine like diethyl ethanol amine. But their reactivity is low. So one could use blended solutions. One could use low concentrations for primary amine or polyamines. Some examples could be diethylene polyamine. Very small amount of these polyamines accelerates the reactivity of a tertiary amine. Another good example is piperazine, which has high reactivity. Or one could use amino acids like glycine, arginine, sarcosin, taurine, along with a tertiary amine. If the reactivity of the tertiary amine is low or its rate constant is a small number in comparison with monoethanol amine, why would anyone use a tertiary amine? Because the major amount of expenditure in the whole operation is the regenerative energy that needs to be supplied. The regeneration energy of absorbent, which is the tertiary amine, is much, much lower than that of a primary amine. Because the product is a bicarbonate. We know it can be easily reversible. So one can use any of these. One could use amino acid. Why would somebody use an amino acid? Because it is again green. The pollution due to the absorbent reduces. Having said all of these things, how do we design the equipment? How do we design the absorber, the regenerator? What are the different parameters that I need to evaluate? We need to find out the optimum concentration of the amine in the solvent. The primary solvent is water, and you add the amine into it. The concentration of amine is very less. It can be around 2 molar or maybe 3 molar. And you could use very small amount of say 0.1 molar or 0.5 molar of these blended additives which will enhance the reaction. So we need to arrive at the optimum concentration of the amine in the solvent to obtain our degree of separation or absorption of carbon dioxide. The next thing that one needs to calculate is how much is the regeneration energy to be supplied. As I said, that contributes to the major expense of the operation. What will be the concentration of carbon dioxide in the stream which leaves the absorber? We wouldn't want to work towards 0% carbon dioxide. It wouldn't be economical and not essential. Knowing the requirements, we should be able to calculate. What should be the column dimensions for it? The height of the column, the dia of the column. All of these things, parameters, can be evaluated and optimized by performing experiments on kinetics and equilibrium studies. This is an experimental setup. It's a stirred cell reactor used commonly to study the kinetics of the reaction. It is a very easy to operate setup where one would feed the absorbent solvent into the jacketed glass vessel and feed the gas from the gas reservoir where the reaction takes place. And the progress of the reaction is measured with the help of measuring the pressure of the gas in the vessel as the reaction progresses, which can be done with the help of a pressure transducer and a data acquisition system. The fall in pressure data helps one to calculate the rate constant, the order of the reaction, and so on. The same setup can be used to calculate the physical properties like the mass transfer coefficient, the solubility, the physical solubility of the gas. We also need to measure the vapor liquid equilibrium data or the XY data of the system. For that, we could use a system like this. This is again easy to operate system. Here we will feed the loaded absorbent into a vessel, and the gas is recirculated using a simple fan. The entire system will be placed inside a constant temperature bar, depending on the temperature at which one needs to measure the vapor liquid equilibrium data. These are ionic reactions, and therefore the measurement of conductivity using a conductivity meter ascertains the reaching of equilibrium. If the conductivity reading remains constant for a period of 6 hours, the equilibrium is assumed to have attained. Further to which, the system is switched off, by which I mean the heating and the fan is switched off, and the sample from the liquid phase and the gas phase are analyzed to know the composition of carbon dioxide at that temperature condition, the composition of carbon dioxide in the liquid phase and the vapor phase. This experiment may be repeated at different temperatures and different loading conditions to generate the vapor liquid equilibrium data. Once we have the vapor liquid equilibrium data and the kinetic data with us, we are now enabled to design the column for our conditions. Having said all of this technology of reactive absorption of carbon dioxide for carbon dioxide capture is already implemented in India and abroad. The first carbon capture, storage, utilization plant in India was commissioned in November 2016, capturing carbon dioxide at around $30 per ton, when at the same time the other parts of the world captured carbon dioxide at almost double the cost. The beauty of this plant is that the captured carbon dioxide is entirely used by the Teutocorin alkali chemicals and fertilizers adjacent to it for their soda ash production. The technology is provided by the Carbon Clean Solutions Limited, This is a zero emission plant. Let us look at another one. This is the Shell Canso carbon dioxide capture for Lanxess chemical facility commissioned in October 2030, Q3. Lanxess Chrome Chemicals production facility in Newcastle, South Africa is designed to capture 481 cubic meters of carbon dioxide per day. Shell Canso also has supplied technology to various other parts of the world where plants are commissioned and some are in progress. Having said all of this, let us look at the carbon dioxide concentration. The Keeling curve by the Scripps Institution of Oceanography at University of California, San Diego, which they generate has their observatory at Mauna Loa, Hawaii. The Keeling curve gives us the concentration of carbon dioxide. The curve gives us a daily record. The y-axis gives us the concentration of carbon dioxide in parts per million, and the x-axis is the timeline. The concentration on 30th July 2020. This is a 6-month average. Was 413.28 parts per million. Let us look at another curve. Few days later, on August 3rd, 2020, this is their curve on an hourly basis. And the carbon dioxide reading was 413.75 ppm. This makes us think the need. With the vertical mobility of mankind, energy consumption has increased and is increasing by the day. Energy production accounts 80% of the carbon dioxide emissions. I mean the anthropogenic, man-made emissions of carbon dioxide. 80% is due to energy production. According to the International Energy Agency, the carbon dioxide emissions are projected to increase by 60% between the years 2013 and 2050, without substantial attempts to stabilize the atmospheric concentration of greenhouse gases. The average global temperature will rise above the pre-industrial levels by 5.5 degrees Celsius in the long term and almost 4 degrees Celsius
What the?
Maybe there seems to be some problem with the broadcast. Narayan, can you put the spotlight on me? I'll take the questions.
Yeah. Sorry.
Or the presentation has stopped abruptly. On YouTube, it is not seen. Narayan, can you please?
Yeah, you're a spotlight. Ma'am, Meet has joined.
Yes.
I'm starting again.
From where you stopped?
I paused where I left the meeting.
Yes, please do it immediately. Thank you. Questions, I would be glad to address. Thank you. Thank you, ma'am, for such a thought-provoking session. Ma'am has elaborated the carbon dioxide as a greenhouse gas, carbon dioxide capture from the industrial processes as a mitigation methods, processes to capture the carbon dioxide, how to design the process, parameters affecting the design, and where it has been implemented. The need of the hour is we chemical engineers should join hands with other disciplines to address carbon dioxide mitigation for sustainable living. Thank you once again for such an insightful presentation. Participants are requested to write the questions in chat box if any. Ma'am will try to address all the questions. In case it is not possible to cover all the questions because of the limited time, we will answer your questions by email.
Come on.
May I please know if there are any questions?
Can we ask you some of our own questions?
Yes, please. Can you be little clear because we already faced problem with the broadcast?
Yes, ma'am. Yes, ma'am.
Here
Yes,
with
ma'am.
question. Thank you.
Yes, ma'am. Am I audible now?
Yes, please go ahead.
Yes, ma'am. So, ma'am, when do you think is the physical solvent used for carbon dioxide absorption?
Okay. I will restate the question for the sake of the audience. When will one use a physical solvent? That was the question, if I understood it correct. Physical solvents are used when the concentration of carbon dioxide in the inlet gas is very high. In the presentation, I had told that the concentration of carbon dioxide in the inlet gas is around 14% for the flue gas from thermal plant. In such cases, we cannot use physical solvents. When we use physical solvents, the operation that takes place is entirely physical absorption, or the driving force is the concentration difference or the delta P, pressure difference. Therefore, the concentration of carbon dioxide in the inlet gas need to be high. It can be physical solvents are used when we have like the inlet pressure something more than 414 kilopascal. We know that the standard atmospheric pressure is 101.325 kilopascal, which means 4 atmosphere, a little more than 4 atmosphere pressure. That higher pressure, I can go for physical solvent so that the rate takes place. The rate, which is the driving force upon resistance. My numerator, my driving force has to be favorable. I hope I have answered your questions. You are free to
Yes,
ask
ma'am.
any other questions in the chat.
Yes, ma'am. Ma'am, we have a question here from Dr. Jyoti Tope. Her question is, what components are used as carbon dioxide scrubbers?
As carbon dioxide scrubbers.
Yes, ma'am.
Let me just rephrase the question if I have understood it. What I have understood is that the person wants to know that what kind of a solvent would I use for carbon dioxide removal or absorption. I would use, suppose if the concentration of carbon dioxide is less, then I need to choose a chemical solvent. So what is the condition of this chemical solvent? The chemical solvent should be such that the reaction has to be regenerated, or the products of reaction of carbon dioxide with the absorbent, the solvent, should be easily dissociated. Only then I can go for a regenerative process, and that is essential to make the process sustainable. I hope I have answered the question. Is there any other question?
Yes, ma'am. Ma'am, we have a question here from Neha Sundar. Her question is, what is the most effective way of carbon capture?
Okay, thank you. This is a very good question. I would say that I have read about adsorption, and people are doing adsorption, but chemical absorption now is specifically not absorbing from the atmosphere. Chemical absorption are from single point sources of carbon dioxide, or in other word, from industrial emissions. So from industrial emissions, we would go for reactive absorption or chemical absorption. As I already stated, if it is a good pressure, very high pressure, we can go for physical solvents. We also know that there are membrane separation. Now, membrane separation is not for carbon capture for managing the concentration in the atmosphere. This is for small amounts. So, the method for industrial emission would be by reactive absorption. I think we can take one or two questions, and the rest we will address on the email, because we would like to go on, but the next, can you ask me a question or two if you have any?
Sure, ma'am. So, ma'am, why do people talk about the use of tertiary amines for absorption?
Tertiary amines, okay. Now, tertiary amines are those absorbents which form bicarbonates as a product, which means the energy that I need to spend in the stripper or the desorber. You saw in the presentation the second column, the regenerator. there the energy that is required is very less because the products are bicarbonate. Therefore, I need to spend less energy for regeneration. However, there is a caution. The tertiary amines, the rate of the reaction is very less. Therefore, when tertiary amines are used, say for example, methyl diethanolamine, one would add very small quantities of other primary or secondary amines or polyamines to enhance the activity. That would be in very small amount. If the main amine, in this case in your question, tertiary amine, is like around 2, 3 or maybe even 6 molar, we don't need to go up to 6 molar. We can use something like 0.1 to max 0.5 molar of the additive. So blended amines with tertiary amine being the main solvent is a good option which has high reactivity coupled with low energy of regeneration.
Thank you, ma'am, for enlightening us. Ma'am, we have another question from Dr. Jyoti Tope. Her question is, can microorganisms be used for clearing air pollution or polluting gases, that is bioremediation?
Yes, it can be used. That is a very good option, and people are working on it because they are living organism. We all know there is much to be done to manage it. Due to paucity of time, I would request you to please post your questions on chemical.dept@thadomal.org and we will surely get back to you. Thank you so much for listening to this presentation. We will wait to hear the next speaker. Thank you.
Hello, friends. My name is Pranav Maskov, and to quickly introduce myself, I started my journey in chemical engineering from Thadomal Shahani Engineering College, also called as TSEC. Then went ahead to do my master's again in chemical engineering from Ulm University, Germany. And I'm currently pursuing a PhD at Fraunhofer Institute of Chemical Technology, which is one of the largest organizations in Europe that is dedicated to applied research. Needless to say, that with this profile, I was amongst the few who chose chemical engineering, and not because there was no other choice. For me, chemical engineering at TSEC was a roller coaster ride. I still remember my first day at TSEC when I went to the department to see what chemical engineering actually looks like. And that's when I realized that chemical engineering is completely different from what we study in high school chemistry textbooks. As I continued my journey for 4 years at TSEC, I realized that chemical engineering is a vast discipline of engineering, but at the same time, it is the only discipline which connects micromolecular sciences with the macromolecular ones. Let me explain this with an example. We all must have mugged up chemical reactions when we were in high school, but with a strong foundation in chemical reaction engineering, you can actually try to engineer these reactions and then unravel the secrets of nature. This is one of the many applications of chemical engineering and personally my favorite. Mm, the faculty at TSEC is well equipped with their fields of specialization, and they will always help you get a holistic picture of chemical engineering and will allow you to choose for yourself which domain you want to specialize in. They emphasize a lot on practical training and are really very cooperative. Practical training is extremely important if you want to make a good career in chemical engineering.
I was lucky enough to intern at a couple of firms, Vasu Chemicals being one of them, and then I decided that sustainable chemical engineering is my calling, is the domain that I want to specialize in. During my post graduation and my early PhD phase, like whatever time I have spent so far in my PhD, I have realized one thing, and that is the chemical industry is at the hub of the global industrial network, and sustainability in the chemical industry is eventually going to lead to a sustainable world. In order to address key environmental problems, chemical engineers with an innovative mindset and an appropriate skill set are required. Chemical engineering at TSEC is going to give you an atmosphere that will foster the innovative mind that you will bring along, and they will polish you with an appropriate skill set and eventually prepare you for the challenges that you have to face once you're out of TSEC. So, with this, I would like to stop and I would like to let you experience this exciting webinar that the Faculty of Chemical Engineering at TSEC has organized. If you have any further questions, then please feel free to contact me on the email address below. Until then, bye bye and take care.
It is my pleasure to introduce Mr. Tushar Jhaveri, our own alumnus from 1988 batch. He has also completed his Master in Material Science and Engineering from University of Florida. He has been honored with Outstanding Service Award, NES International India Section. He is Chief Executive of Vasu Chemicals since 1992. Vasu Chemicals is known to be a pioneer in industrial wastewater treatment. He is the mastermind behind Halliburton Vasu Chemicals LLC, which mainly deals with refinery process treatment. He is a member of American Institute of Chemical Engineers. He has held many high posts of responsibility in NES International. Now I request Mr. Tushar to share his expertise in industrial wastewater treatment. Welcome, sir.
Good morning, everybody. This is Tushar Jhaveri from Vasu Chemicals. I am from the Thadomal Shahani Engineering College, Chemical Engineering batch of 1988. I am very thankful to the college for inviting me today to deliver this talk on industrial water treatment. My agenda today will include the following topics: introduction to water, sources of water, water and its treatment, the important parameters that we monitor, and the different types of industrial water treatment, the future growth that we expect in the coming years, and then we can follow up with an open Q&A session. Water, like we all know, is everywhere. It is used in municipal, agricultural, industrial use for a wide range of essential applications. It's the key to our lives. Efficient use of fresh water, management and control of processed water, and reuse, recycle of wastewater is the key challenge for India as our population grows and economy develops. This is a very scarce resource and we need to manage it very carefully. Today we will focus only on industrial water and its treatment to maximize its efficient use. Water is used in every single industrial sector, including oil and gas, petrochemicals, fertilizer, power, infrastructure, textile, chemicals, hospitality, and more. It is having several uses in the industry, for example, for cooling, for steam generation, often used as part of the manufacturing process as well as a raw material or as a solvent in the actual process of the industrial unit. Hence, the treatment of water can be classified into the following for industries. One is cooling water, boiler water, processed water, and waste or effluent water treatment. So, we all know the sources of water, but the fresh water source is rain and the water cycle. The sources will The rain will go to the surface water, which is the river, lakes and dams, groundwater, which is the borewell. We also have RO water, which is the desalinated seawater, and we also have recycled water from the wastewater treatment plants and the sewage water treatment plants. So these are typical sources that an industry would have access to. The water cycle is most critical. We are well aware of this. I guess we have learned this right from our school days, where the evaporation from the oceans and the land goes into the clouds, and the condensation of the clouds, precipitation leads to rain, and the water again runs off with the rivers into the water table and into the sea. So this is a cycle that sustains mankind, is the source of our lives and very important for us to survive. Natural water, when it runs through the soil, will have a lot of ionic impurities. The river and surface water will have less, well water will have less organic contamination, and all these impurities vary with season, more so for surface water. If we look at the hydrological cycle, more than 97.6% of the water is in the oceans. The rest is divided into the ice caps, the glaciers, and the groundwater, and the lakes and rivers, and even the atmospheric moisture. But primarily our water is all stored in the oceans. If you compare the groundwater, the surface water with the groundwater and the sea water, you will see that the temperature, suspended solids, turbidity, organic oxygen, dissolved oxygen, and salinity vary substantially. And these are very important factors when an industry selects its source. Water and its treatment is very critical. Water is a universal solvent, as it is known everywhere. It dissolves salts and gases as impurities, and impurities are present in varying quantities. Nature and amount of impurities in the water imparts the different characteristics to the water. This varies seasonally, even within the same source, and poses different problems in different applications. Hence, water treatment. This is a very vast field and deals with removal of impurities from water and makes it suitable for the end application. And nearly all of these kind of treatment involves use of some chemical technology expertise and of course monitoring. This is very key, and that is where chemical engineering plays a very key role in water treatment. So broadly we can divide water treatment into the different segments. First is the physical part, which includes just physical treatment of water, which would be filtration, clarification, or aeration. There could be external treatment of water, which is disinfection, softening, demineralization, dealkylation, or even reverse osmosis. And then there is the chemical treatment of water, which is something that I will talk more about today. Managing the impurities in the water is very key, and water treatment is thus the process of making water suitable for its specific end use. We cannot change the water, but we can change the way it affects our use in the industry, and that is water management. This ensures that impurities in water do not adversely affect the production or the operation of the industrial unit. So the focus of water treatment always is to identify which of the impurities would cause these kind of unwanted effects, and then taking necessary steps to either remove the impurity, which would be physical, or mitigate the unwanted effect, which is typically a chemical treatment. So this is how the impurities management can be broadly understood. So what are the primary water parameters that we would look at when we consider water treatment? Very basic again: color, odor, taste, suspended solids, turbidity, pH, alkalinity, equivalent mineral acidity, chlorides, sulfates, hardness, calcium, magnesium, sodium, iron, silica, TDS, conductivity, oxygen absorbed, COD, BOD, total organic carbons. I will touch on a few of these critical parameters that play a significant role in industrial water treatment. Color. This is very important because indicates the presence of undesirable, dissolved, colloidal, and suspended impurities in the water. For example, if there is iron present in the water, you will see a slightly brownish or reddish tinge. Manganese would make it black, and if you have organics, then there will be a slight yellowish tinge. Color is again very important because it gives an aesthetic value to the water and also potability. If you had water which had slight coloration, you would never drink it, right? So color of the water is very important for it to be clear and transparent for use. Odor and taste is also very important because it indicates undesirable impurities, maybe such as hydrogen sulfide or sewage contamination, etc. This is an important water parameter, especially in the food and beverage industry. They don't want the water that is being used to impart any odor or color to the final food that is being produced in the industry. All matter suspended in water large enough to be retained on a filter paper are called suspended solids. These are the undissolved solids in the water. Turbidity indicates the extent of cloudiness or muddiness of the water. It is again caused by the suspended and colloidal matter. Can be inorganic or organic origin, but something that hinders the passage of light causing turbidity. So this is also a very important parameter used in water treatment. Total dissolved solids are the total content of the dissolved matter in the water. It represents all the charged ions and also the uncharged ions and the molecular species of the same. As a summation, you can say the cations, mainly calcium, magnesium, sodium, and anions would be bicarbs, chloride, sulfates, and silicon. Conductivity is also a very quick and important measure. It is a true indication of the purity of water. Higher the conductivity, higher the content of the ions, and higher the impurities of the water, and vice versa. An empirical formula does exist between electrical conductivity and the total dissolved solids, and this conductivity is also very temperature sensitive and very important, affects the corrosivity of the water. pH is another basic parameter. We have all learned this, we have all analyzed this in the lab. It's a well-known parameter of water. Water dissociates into H and OH minus, and negative logarithmic of this is pH scale, and it is a scale, empirical scale from 0 to 14, where 7 is a neutral point, and below 7 is the acidic area, and above 7 is the alkaline area. Alkalinity indicates the quantities of bicarbs, carbs, and hydroxide in the water, or the alkaline salt content of the water, as it is sometimes referred. It is the amount of acid necessary to neutralize the carbs, bicarbs using two indicators, phenolphthalein and methyl orange. And hence we have the methyl orange alkalinity or the M alkalinity, or we also have the P alkalinity, which is the phenolphthalein. This is a neutralization curve, and which kind of shows us where the alkali stands, where the P alkalinity stands. P alkalinity starts at about 8.3, 8.2, and M alkalinity is at 4.2. So we can see that below 4.2 is a pre-mineral acidity, and above 8.3 is the regime where you have more of the hydroxides. So this is a very important curve that is used in industry to understand what kind of ions are contributing to the alkalinity in the water. Total hardness again is very important. It helps us to assess whether the water is alkaline. The water has a soft water or a hard water. Part of the total hardness is associated with alkalinity in water and is referred to as alkaline hardness, carbonate hardness, or even temporary hardness. The balance is associated with the mineral acidity of the water and is called the non-alkaline hardness or the permanent hardness. So this is again very important for selection of water sources. Organic matter plays a very important role and impacts water usage everywhere. It covers all substances in water susceptible to oxidation and expressed by various indices, some of which are commonly used in industry, like the COD and the BOD. The COD indicates the organic matter dissolved by non-acidified potassium bicarbonate and covers majority of the organic compounds and oxidizable mineral salts. whereas the BOD represents the amount of oxygen used by microorganisms consumed by biodegradable water in wastewater using aerobic conditions. Generally, for BOD analysis, sample is incubated for 5 days and the result is reported as BOD 5, the 5 being in the subscript. We now come to the various types of industrial water treatment: the cooling water, the boiler water, the processed water, and the wastewater. This is a typical schematic of the cooling water circuit. As you can see, this part here represents the cooling tower. The cooling tower has makeup, it has flow down, and it has evaporation from the top. This cooling water is pumped through the recirculating water pumps into the plant where the heat exchangers are there and the cooling is taking place of the processed fluids. And then the hot water which is coming out of the heat exchangers goes back to the top of the cooling tower for cooling and again recycled. That's why it is called a recirculating type of system. While recirculating, there are a lot of problems associated with this water, and these can lead to problems in heat transfer of the equipment in the plant, and these include corrosion, scaling, and microbiological problems. These are both interdependent and interinfluencing, and it is important for any industry to ensure proper control of these problems to ensure optimum usage of the cooling water circuit. So, these are the factors that are important which need to be considered while selecting a water treatment program, which is the proper site temperature, the metallurgy of the heat exchangers, the water box, the pipelines, the fills in the cooling tower. The fills are the packing in the cooling tower where the heat transfer takes place between the hot water and the air. And of course, there should not be any contamination coming into the cooling water system. So we first talk of the corrosion prevention in cooling water systems. The most important is selection of proper metallurgy, sacrificial anodes, coatings, and use of corrosion inhibitors. All four are important, and depending on the type of metallurgy plant and the kind of economics that play a role in the selection, proper program can be made. The corrosion process is well known. It occurs due to the presence of local cells with anodic and cathodic sites on the metal, mediated by the electron transfers to an electrolyte. This is something we have tried from our school days, and this process is very, very well established. A lot of research and well understood, and a lot of different types of treatments are available to mitigate this. This includes anodic inhibitors, which are chromates, nitrates, orthophosphates, and molybdates, or cathodic inhibitors like phosphates, zincs, and controlled deposition of calcium carbonate. Chemical treatment for corrosion control again depends on the metallurgy. So, for example, for carbon steel, the typical programs used are the stabilized orthophosphate zinc. For copper and copper alloys, oxidant stable azoles are used, and for sure coatings and sacrificial anodes are used in water boxes, and covers, and tube sheets. The next problem in cooling water systems is scale formation. These are dense, adherent, and dark, hard material composed mostly of calcium and phosphate salts, but usually heterogeneous in nature, and they can precipitate on the heat transfer surfaces and become very hard. Some types of common scales that are encountered are the calcium carbonate, calcium tripolyphosphate, and phosphate. Magnesium silicate scales are very, very hard deposits, very difficult to clean. Magnesium carbonate is more uncommon, more rare to find. But what we see is that calcium salts are the most problematic because we all know calcium has a reverse solubility. So as you can see in this graph, with the increase in temperature, the calcium solubility keeps going down and its propensity to deposit keeps going up. So here you see a heat exchanger that is powered with calcium salts. You can see how it has plugged most of the tube entrances. It Water indices are also used to evaluate scaling or corrosive tendency of water, and it's a predictive tool and very interesting to water treatment engineers because it helps them to select the correct treatment and the correct application of the chemicals. Scale control is very important. Uh, Scale control can lead to reduction in water flow, like I showed you in that other photo. I have this one. Poor heat transfer, reduction in plant load, will require frequent chemical cleaning, unscheduled shutdown maybe if the tubes get choked and the cooling is not happening. And for sure, it will shorten the equipment life because under the scaling you will have again more corrosion, heat transfer restrictions, water flow restrictions. So scale control is very, very critical. There are several ways to do scale control. You have physical methods, which is like softening, and you also have the chemical methods, which include crystal modification, which kind of prevents regular crystal growth and makes them small and softer and irregular, preventing agglomeration. So this is a SEM photograph showing you the difference where crystals are modified with and without after polymerization and without polymerization. The mechanism is usually either of the dispersion kind, or you can also have threshold inhibition. Dispersion is the more common type used in industry. Basically, it changes the charge of the particulates matter so that they repel each other and do not have an opportunity to agglomerate. So this is the normal method that is used in industry for scale inhibition. The third important problem in cooling water treatment is microbiological fouling. The major classes of microorganisms which are associated with recirculating water systems are bacteria, which is in the water, the algae, which grows on the cooling tower structure and distribution deck, primarily because it is exposed to sunlight and with the photosynthesis that occurs on the structure. This kind of algal growth is a very common sight in cooling towers. Fungal growth can also happen if you have wooden structures in the cooling towers, which can lead to delignification of the wood. Mostly now the cooling towers are made of PVC fills, so this is becoming more and more rare. But still, in the older cooling towers, which are still in use in industry, where the wooden structures, louvers, etc. are used, fungal growth is to be monitored. Microbiological fouling and growth is very important in cooling water systems, particularly because a cooling water system, cooling tower is very conducive for microbiological growth because of the temperature in which it operates, the sunlight that is available, and the abundant nutrients that are also there in the circulating water. All these make microbiological proliferation in cooling water a very common phenomenon. So what are the different types of bacteria that we find in cooling water system? This is actually different from potable water bacteria that are typically found because these are generated in the cooling water system. So again, there are two types. One is the aerobic type, which thrive in the absence of oxygen, and one is the aerobic type, which need oxygen to survive. So the anaerobic type are like the sulfate-reducing bacteria, and these typically are under a deposit. So if you see, this is a pipe surface, and you have, this is the brown is the deposit or the corrosion module. Underneath that, you will have under deposit corrosion. And this is where this reaction is taking place. And the H2S is a highly acidic material that is formed by this bacteria, and that is what will cause the corrosion. The aerobic bacteria include the nitrifying bacteria, the iron bacteria, and most important are the slime-forming bacteria because they form a very sticky gelatinous mass which traps the suspended solids and even other bacteria, protecting them from the treatment chemicals. Further, the slime-forming bacteria are also having an insulating effect. So, if you see the biofouling, that is where this topic will be discussed more. The two classifications of the bacteria, broad classifications of the bacteria include the sessile are the one which get attached to surface. And over 95% of the bacteria in the cooling water system are sessile. They live in the biofilms which I explained earlier, biofouling, which kind of forms with these slime-forming bacteria. Now, the challenge here again is monitoring, because when we take a sample of water and when we analyze it, what we are analyzing is the planktonic type, whereas the problems which are caused are more by the sessile bacteria. And this is one of the largest problem in cooling water systems, monitoring of cooling water systems, and something that we need to be very careful about. This drawing kind of indicates how the planktonic cells get attached to the metal, and then the biofilm keeps growing, and this biofilm is protecting all the different bacteria and some suspended matter as well. As the colonization progresses, this is a very typical phenomena that is observed. So why microbiological control? Fouling, you can see the slime formation on the tubes and the heat exchangers. This is a common thing with microbiological growth is hampered. This is highly insulative, sometimes as much as 4 times less thermal conductivity than even calcium scale. So it's very, very critical. It also leads to under-deposit corrosion, which can reduce plant operating loads. It can lead to pitting corrosion, unscheduled shutdown. It will reduce the cooling tower efficiency, and it will damage the wooden parts of many in the cooling tower. So how do we control microbiology? We have 2 types of product ranges for that. One is the oxidizing biocides like chlorine gas, which we use. Even our municipality uses for disinfection of our domestic water. There is also sodium hypochlorite, which people are spraying during this time of COVID. There is bromine, there is ozone, there is chlorine dioxide. There are also non-oxidizing type of biocides, which are shock dose on intermittent basis. These include organosulfur compounds, quaternary ammonium compounds, aldehydes, DBNPA, and carbamate compounds. So a lot of different types of chemistries are available, and again, that's a deep science to understand which is the correct biocide for a particular application, and that requires a lot of understanding and monitoring of the water system. The biodispersion is also very important. If you see, this is the metal surface on which you have the slime or the biofouling with the bacteria and the suspended matter being protected. And these pins are the biodispersion, which is spinning and attacking this biofilm to penetrate and reach the bacteria. And you can see that over time, if the product is working well, it will break up the biofilm into smaller parts which come into the water phase, where it can be killed with the chemicals that are there in the water. So the removal of the biofilm and release of the trapped bacteria in the bulk water is very important. Unless the biofilm is loosened and removed, the bacteria will continue to thrive. So that was a very brief discussion on cooling water treatment. The next is the boiler water treatment. Large part of water used by industries is used in boilers to generate steam, which is we all know required in industrial processes. So there are many types of boilers, but I have just broadly divided it into 3 types. There are many more, like I said. You have the fire tube packet boiler, which has a low pressure boiler, LP is low pressure boiler. Then you have the water tube boilers, which are the waste heat recovery boilers, and these are the medium pressure boilers. These are typically found in most large industries because they help to recover waste heat as well. And then you have the water tube for power and process applications. These are the high pressure boilers, and these are very typically used in power plants. This is a typical schematic of a boiler water system. You start with maybe deamine water or a softened water that goes to the deaeration, and then the boiler feed water pump goes into the boiler drum. This is the whole boiler unit, and then you have intermittent blowdown from the bottom, or you have continuous blowdown from the system, and the steam will go into the power plant. Into the industry plant. If it is a power plant, it will go to the steam turbine, or it will go to the condensers, and then it will go back to the the condensate tank where it is collected. If it's a paper mill, it will go into the paper mill and the steam will be used in the process, and then again the condensate will go here. So depending on the type of the plant, whether it's a power plant or a refinery or a paper plant, the steam is used in the process. That is what this indicates. And then this condensate tank, where the water is pumped as condensate water, it's called the return condensate, and that again makes up as a makeup water, as a feed water in the boiler. It's a very pure water. So this is a typical boiler system schematic. So what are the general problems that we have with such steam generating boilers? In the low pressure boiler, the problems are obviously diminished. We all have corrosion because of the dissolved oxygen and the condensate lines and the damage of the boiler and ancillary place. There will be scale again leading to tube overheat and failure. There will be sludging, the drum is dirty. There will be foaming, so there will be a carryover of impurities along with the steam. It's not the steam, it will wet steam and create more problems, which is called the carryover and the priming, which affects the steam purity. In the medium and high pressure boilers, problems are even more pronounced, which include oxygen corrosion, the caustic corrosion, caustic embrittlement, hydrogen damage, acid phosphate corrosion, condensate corrosion, corrosion product deposition, and silica carrying. Each of these problems have a solution. Each of these problems need a specific operational conditioning so that the boiler is operated safely and in a correct fashion so that these problems are not encountered. Several types of treatment programs again, starting with physical type of treatment where it is important to maintain proper makeup water source. If it is a softening plant or a DM plant or a DM plant based on reverse osmosis, it is important to ensure that the operation of this plant is correctly done so that we do not have slippage of some unwanted ions into the boiler water system. Proper operation of the deaerator is also very important because this will ensure the boiler drum is safe and operating correctly. Oxygen scavengers are also added, which reduce the dissolved oxygen and hence the corrosion. Scale inhibitors are also added to reduce the sludging inside the boiler drum. Alkalinity booster for pH control in the boiler for proper balance is also common. In the condensate line, again, a corrosion inhibitor can be added because that line from the condensate tank to the makeup line again is extremely prone to corrosion because the condensate water is usually very coarse. And of course, the water chemistry needs to be controlled, such as silica, pH, alkalinity, etc. Next is the process water treatment. Process water treatment is again a very wide field and it changes from industry to industry because each industry has a different need and application of process water in its manufacturing. The process water treatment is usually designed, which is very specific to and tailor-made for each industrial process or subprocess. The treatment is designed to meet specific objectives of the plant, which could include quality targets, reduction in operating costs, and improving heat transfer. Examples of industrial processes that require these kind of special treatments are in steel plants, oil refining, coal washeries, textiles, dyestuffs. These are some of the industries that have a large usage of such water. In steel making, there is direct cooling where once the molten steel is converted into briquettes or slabs or wire rods, then they have to be cooled with direct water spray, and that water gets contaminated with the steel and the iron particles. So it requires a very special type of treatment. That's process water treatment. And again, that can be discussed specifically for a specific industry, depending on what are the challenges that are being faced. Last is the wastewater treatment, and we all know why that is very critical. It addresses environmental concerns and an awareness that is increasing every day, and it is important to ensure good wastewater treatment so we don't pollute our environment. there is a huge water scarcity, so its treatment and recycling is important. Quality of life is affected also by wastewater treatment because it can affect our drinking water sources, it can affect agriculture, it can affect our recreation and fishing lives. Industrial reasons are many for wastewater treatment. There are a lot of stipulations by government, pollution control board authority, quality of the water discharge from an industrial unit. So prior to discharge, it is important to have proper treatment so that there is no violation. There can be economical reasons also because sometimes the use of water can be a huge cost saving since that will reduce the usage of the fresh water. There can be social reasons also because the cost to discharge can be high. The discharge consent limits and ZLD is the zero liquid discharge compliance. Many places in India now have the ZLD compliance requirement, and of course the image of the industrial unit also is an important factor. If they are not discharging good quality wastewater into the environment, then they are going to have a problem for the reputation and sustenance in that particular geographic area. A simple wastewater treatment plant layout is this way. The effluent from the industry comes into the equalization tank where we add the alum line and pH adjustment is taking place, and then it goes to the primary clarifier. The polyelectrolyte is added. The bottom of the clarifier is the chemical sludge which goes for dewatering into the centrifuge and then for disposal as a solid waste. The outlet of the primary clarifier goes into the radiation tank, which is the secondary treatment, and this is where the biological treatment, the biological degradation of the waste. Sometimes this is supplemented with bioculture as well. After the secondary treatment, the wastewater is then going to the tertiary treatment, to the secondary clarifier, where all the suspended matter and other biological components are removed, and the biosludge again is going for the dewatering of the bed. And the clear water is then sent either for discharge if it is meeting the environmental compliance, or if it has to be reused, then it goes for tertiary treatment, where typically that will involve reverse osmosis plant to reduce the TDS, to bring the water back to its, almost back to its original quality. So this is a typical layout of a wastewater treatment plant in industrial unit. Like I mentioned, this is the chemical treatment, which is primary, the biological treatment, which is secondary, and the tertiary treatment, which is the reverse osmosis, the sludge handling, which is the dewatering. This kind of completes the presentation on the different types of, the four types of treatment, which is the cooling water, the boiler water, the processed water, and the wastewater. Each of these topics is a topic by itself and needs a lot of study and understanding, and it varies from industry to industry. So it's a very, very wide and vast field requiring versatile knowledge and application techniques. So what is our future growth? What is the next generation water technologies? Many times people are asking us, okay, where does India stand as compared to the rest of the world? What is the research going on in water? How do we save usage of industrial water? How do we ensure discharge of industrial water is not affecting our environment and our future generations? So what are the growth drivers for the future? That is important for us to understand. So there is a lot of investment happening in developing newer water technologies, which is obviously driven by rising population and increasing demand, and which is all leading to a scarcity of water. Pollution and climate change, environmental concerns, these are also very important to us now. The digital revolution which has started coming in is also driving a huge change in the way water treatment applications are employed by the industry. For example, there are a lot of low-cost sensors, meters, and monitoring technology, so that remote monitoring of the water quality can be done. Large volumes of data are analyzed by artificial intelligence and machine learning systems. These are playing a very key role, and I think this is going to be the future, not only in India but all across the world. And India is playing a very key role in the development of these technologies. Water treatment and water resources scarcity is probably the number one driver. There are many countries, geographical areas, like if you look at Israel or you look at any area which is very arid or like surrounded by deserts, they realize the value of water treatment more than anyone else, and a lot of development in water technologies are done in these kind of areas because it is absolutely required to sustain life. So some of these areas where these new technologies are being applied and newer processes are being developed, not only in industrial R&D divisions but also in universities and private research labs, is including reverse osmosis, desalination, sewage and effluent water, reuse and recycle. Very, very important. We have now many cities which are called smart cities, where sewage water is treated by the municipality and brought to a more acceptable level and then sold to industry. One of the biggest and most successful example of this would be Chennai city, where most of the sewage and effluent water is recycled and very well treated by the city, so that the water scarcity impact is diminished. There are a lot of other smart cities as well in India which are either on the road to this kind of reuse and recycle or have already achieved that. So it's a very encouraging battle that we are fighting to combat water scarcity. The environmental concerns, the technologies to address the environmental concerns are also important. This will require enhanced effluent treatment, disinfection, because if it is going to come in human contact, then definitely we need to ensure that it is well disinfected and the water quality is fit for human consumption. We also have industrial units that follow a zero liquid discharge, and this is something that is very positively developing in our country, and a lot of units are now opting for this, and hopefully this will become also a norm by the authorities in the future. All this will require innovative chemistries and methods for water treatment, and a lot of developmental work in developing these kind of chemistries, these kind of application methods is the need of the hour, and is the focus of several research groups across our country. The future for the digital technologies is also very, very important. Using the data and the AI to get predictive insights for asset maintenance, water quality, predictive water quality upsets, and increasing operating efficiencies and downtime is the key to this. So you can imagine if you have an industrial water system, for example, a typical refinery in India uses close to, if you look at fresh water, maybe about 2,000 meter cube of water per hour. So that is about 20 lakh liters of water is used every hour. So if you start analyzing this kind of water for the different parameters, and you start collecting data over time, you can understand it's an immense amount of work to analyze and interpret the trends and the impacts of the changes in the water quality, like purities and associated things. Analyzing this kind of big data is something that is becoming more and more relevant, and particularly in times like this when people cannot travel or visit the sites physically, remote monitoring and remote analysis and interpretation of data is becoming more and more important. And we are seeing a lot of companies investing time and resources to develop very effective digital tools for not only data acquisition but also for data monitoring. And to do all this, it is very important to have remote monitoring to enable access to the water tracking in rural remote areas. So these are all going hand in hand and very important for us. And we hope that a lot of the young engineers and students who are with us today will be the future leaders in the development of these technologies and will play a key role in sustainability of this very important resource, which is so critical for our lives. Water, whatever we can do for saving this precious resource is never going to be enough. So with that, I will end my presentation, and I thank you all for your attention and patience. And I'm now open to any questions or discussions that you might have. Thank you.
Hello, sir.
Hello.
Yeah, we have a few questions from the audience. One of the questions is from Manoj Kumar Das. Which technique is very effective for water treatment?
Which technique for what kind of water treatment? Can you please elaborate?
That's all he said, so I'm not sure.
Yeah, I think there are a lot of techniques, but it depends on what kind of treatment, whether it's cooling water, boiler water, waste water. So I think it's an incomplete question.
Okay, he can ask on email if he has any further doubts.
Yes.
Or if he wants an elaboration. Another question is from Munendra Patel. Can you please elaborate the role of superbug in water treatment in oil refinery?
Role of superbugs in oil and gas. Okay, yeah, sure. I mean, this is a technology that we are seeing some people use, but it's not yet found, I would say, a common application so far. It's very expensive and it is very specific. So it requires a lot of pre-testing to make sure that these kind of superbugs will be applicable for treatment. But yes, we are seeing that more and more in wastewater treatment, where these kind of specific bugs are being used in the secondary treatment, biological treatment, to focus on a certain contaminant which may not be getting degraded by normal processes. For example, people who have effluent with cyanide may find it very difficult for secondary treatment. So there are companies which have developed these bugs which specifically can degrade cyanide kind of waste. So like this, specific bugs are also prepared, and general bugs, superbugs are also prepared. So yeah, it's an exciting field, and I expect a lot of developments to happen in this in the future.
Okay. There's another question. What are the methods typically used in industry to remove color and odor?
Color and odor. So color can be removed only with physical measures like filtration, and that is if there are suspended matter which can be removed. So that is a physical way of treating it.
Chemically, if the color is due to some organic material, then we have to do an oxidation process like chlorination, etc. So if you add an oxidizing chemistry, then it will react with the organic material that is imparting the color, and then degrade it to make the water more clear. Uh, there are a lot of ways to do this, but it depends on what constituent is imparting the color. With regard to the odor, it's much more difficult. Again, that will need biological treatment of the water, uh, degradation of the constituent which is imparting the odor. So that is very important. There are some chemical methods also to control odor, but for example, if it is just H2S, then you can finish it with something like hydrogen peroxide to remove the H2S. But again, like I said, it depends on who is contributing to that problem, and accordingly, a solution can be found.
Okay. This question is from Dr. Jyoti Tope. What is the role of biosensors or other sensors in determining water quality, and where are these sensors installed in treatment plants?
Sorry, can you repeat the question? Biological
Yeah.
sensors.
Yeah, biosensors or other sensors in determining water quality, and where are these sensors installed in the treatment plants?
Uh, there are a lot of type of sensors that are used today in the industry. For biological online, there are two types of things that we are using. One is called a bioprobe, uh, which basically captures the gives us an opportunity to capture the sessile bacteria and then do a visual and quantified inspection of the food. There are also now online biofouling monitors sensors, which kind of measure the impact of the biological growth in terms of, say, pressure drop across a certain section of the operating unit. And these are typically installed on the return line of the water that is going through the cooling tower after the cooling process has taken place in the plant.
Okay. This question was from Neha Sundar. How to reduce the BOD level of an already polluted water body?
Biological treatment.
Yes. Okay. There are other few questions. Can you please elaborate on role of AI in wastewater industry?
Uh, it's a very, very wide field and a lot of work going on. But basically, AI can be used if you have, for example, influent water sensors, which are detecting over time what is coming in from a particular plant and how the degradation takes place in the wastewater treatment plant. Then AI can be used for future predictive modeling, where it will adjust the chemical dosing or the operating units in the wastewater treatment plant based on changes in the influent water quality. Because we all know the influent water quality is not constant; it keeps changing. So today, what is happening is that either people are doing offline analysis or online sensors, and based on those results, they are adjusting the operation and the chemical dosing. But if we had an AI-based system, then the system would do this on its own by recognizing what are the changes and what are the corresponding actions that would be required. There are companies which have started doing this now.
Okay, and this is the last question. What polymers can be added to inhibit scale in industry?
There are several types of polymers. The two most common chemistries that are used, which form the backbone, are the polyacrylates and the polymalates. The acrylates are obviously made from acrylic acid, and the malates are made from malic acid. Then these are first the starting block is the homopolymer, and then from the homopolymer people make copolymers with something like a sulfonic acid branch. There are also terpolymers. There are also quad polymers. So it's a huge range of products that that are available for water treatment. And different types of polymers are specific for dispersion of different kinds of inorganic material. For example, copolymers of acrylates are known to be very good dispersants for calcium phosphate inhibition. Other polymers of acrylates are known to be very good dispersants of iron and silica. So, homopolymers are more for calcium carbonate basic scale inhibition. So, again, it depends on the kind of water quality and the propensity of the scaling that has been observed in the past, which will determine the selection of the polymer and the type of chemical.
Okay. There's one last question, if you don't mind.
Sure.
This is by Jitendra Malusare. Among different disinfection technologies for potable water treatment, which technique is most effective against all class of microorganisms, including protozoa, bacteria, viruses, etc.?
Uh, it's a good question. Uh, our talk today is more for industrial water, but I can share my knowledge on potable water as well. If you see what people are selling as disinfectant or this kind of water purifiers in the market, you get things with the UV, you get things with ozone, you get purifiers which are based on some chemical addition like chlorine dioxide also now. So a lot of options are available. It will primarily depend on the kind of and the extent of organisms that you have. Is there something which will ensure 100% kill? No, there is nothing which will ensure 100% kill. So to get if somebody is saying that you're getting 100% disinfection of potable water, I don't think that's feasible. There is a way to safeguard water before it is used for potable use, and there are very good laid out WHO standards for this, and that's what typically people follow. Nowadays, you must be also seeing that the people making the companies manufacturing the purifiers are also giving some kind of accreditation, and they mention that our purifier is approved by so and so regulatory body or some kind of lab or something. So lot of marketing hype also goes into this. So we have to be careful on what we are accepting to put into our body. So I would say the most commonly used things are UV and also oxidizing biocides like chlorine or chlorine dioxide.
Okay, thank you so much, sir, for clearing all our doubts.
Thank you. Thank you for this time. Thank you. Shall I go ahead and disconnect?
No, sir, just a second.
I now request Professor Neeta Mehta to thank Sir for that informative session. Thank you, sir. It was such an informative presentation. Sir has covered various aspects of the industrial wastewater treatment, current trends, next generation technologies, and the growth drivers for future. Sir has also shed the light upon digital revolution, the role of AI in wastewater industry, and enhanced effluent treatment like RO disinfection to preserve water, which is fit for human consumption for future generations. The most important takeaway from this session is the remote monitoring and the remote analysis, where the digital technology will play a vital role. The chemical engineering and the digital technology will go hand in hand. Once again, I thank you, sir, on behalf of the organizing committee for your valuable time and inspiring session. Thank you, participants, for the patient listening. See you tomorrow.
Thank you for having me. Goodbye.